Imagine a vast, swirling cloud of gas and dust, billions of miles across, hanging in the cold void of space. A nebula pregnant with potential, ready to birth not just a star, but an entire solar system. What cataclysmic event triggered this cosmic dance? And how did our humble Earth emerge from the fiery wreckage? Buckle up, because we're diving into the heart of the universe's greatest creation story, where gravity plays God and chaos reigns supreme. But hold on, by the end of this part, you'll be left wondering, could a single devastating collision rewrite everything we know about our planet's infancy? Our journey begins about 4.6 billion years ago, in the aftermath of a supernova explosion that scattered heavy elements like iron and silicon across the galaxy. These remnants mixed with hydrogen and helium in a molecular cloud, the solar nebula. Gravity, that invisible architect, began pulling it all together. As the cloud contracted, it spun faster, flattening into a vast disk, the protoplanetary disk, with a bulging center destined to become our sun. At the core, temperatures soared to millions of degrees, igniting nuclear fusion. The proto-sun blazed to life, blasting away lighter gases with its solar wind. In the disk's inner regions, where Earth would form, rocky particles, chondrules and dust grains, clumped together through electrostatic forces and gentle collisions. These grew into pebbles, then boulders, in a process called accretion. Runaway growth kicked in. Larger bodies gravitationally attracted more material, snowballing into planetesimals, asteroid-sized chunks hurtling through space. Earth's zone, about 93 million miles from the Sun, was a hotbed of activity. Silicate rocks and metals dominated, while ices were scarce, unlike the outer solar system where gas giants like Jupiter feasted on volatiles. Simulations from NASA's Goddard Space Flight Center suggest this phase lasted mere millions of years, with Earth reaching about 60% of its mass in just 3 to 5 million years. But it wasn't smooth. Violent impacts released immense heat, keeping the young planet molten. Radioactive decay from elements like uranium added to the inferno, melting iron that sank to form a core. By 4.54 billion years ago, Earth had coalesced into a protoplanet, but it was no paradise, a seething ball of lava oceans under a thick, hazy atmosphere of steam and volcanic gases. Zircons from Western Australia, dated to 4.4 billion years old, hint at early crust formation, but the surface was repeatedly resurfaced by impacts. The late heavy bombardment loomed, a barrage of asteroids that would scar the planet. Yet amid this hellscape, water began to arrive. Comets and water-rich asteroids delivered the building blocks for oceans, degassing from the mantle. The faint young sun paradox puzzles scientists. Our star was 30% dimmer, yet Earth didn't freeze solid. Greenhouse gases like carbon dioxide and methane trapped heat, creating a steamy greenhouse world. As we wrap this chapter, picture Earth as a fiery adolescent, its fate hanging by a thread. But what if a rogue world, the size of Mars, smashed into it? Would it destroy everything or create something miraculous? What if the moon, that serene silver orb in our night sky, was born from the most violent catastrophe imaginable, a planetary smash-up that nearly tore Earth apart? In our last dive, we left a molten Earth teetering on the edge. Now prepare for the ultimate cosmic demolition derby. This isn't just history, it's a thriller where survival hangs on a razor-thin margin. But beware, by the end, you'll question if Earth's scars from this era still echo in our world today. Fast forward to about 4.5 billion years ago. Earth, now roughly its current size, orbits in a crowded neighborhood. Enter Theia, a Mars-sized protoplanet on a collision course. Computer models from the University of Durham and NASA's Ames Research Center reconstruct the scene. Theia slams into Earth at a glancing angle, vaporizing both surfaces in a titanic explosion. Trillions of tons of molten rock and metal eject into space, forming a debris ring around Earth. Within hours, this ring coalesces. Gravity pulls the material together, birthing the moon in a mere day or two, a process captured in high-res simulations published in Nature. The impact's energy melts Earth's mantle anew, creating a global magma ocean hundreds of miles deep. Iron from Theia's core merges with Earth's, enhancing our planet's metallic heart and kickstarting the dynamo that generates our protective magnetic field. Post-impact, Earth's rotation speeds up. A day lasts just 5 hours. Tides from the newborn moon gradually slow it to our 24-hour cycle, stabilizing axial tilt for milder seasons. Geochemical evidence matches. Moon rocks from Apollo missions share isotopic fingerprints with Earth's mantle, proving their shared origin. But Theia wasn't alone. This era, the Hadean, was pockmarked by the late heavy bombardment around 4.1 to 3.8 billion years ago. Asteroids and comets, perturbed by Jupiter's migration, rained down, cratering the surface and delivering more water and organics. Earth's atmosphere evolves amid the chaos. The initial nebular mix of hydrogen and helium escapes, replaced by volcanic outgassing. Carbon dioxide, nitrogen, water vapor. No free oxygen yet. It's a reducing world, perfect for prebiotic chemistry. Oceans form early. Hafnium-tungsten dating suggests liquid water by 4.4 billion years ago, pooling in basins as the crust cools into basaltic plates. Plate tectonics hints at starting here, driven by mantle convection. Early continents like tiny islands of granite poke through lava seas. But life? Not yet. Conditions are sterilizing. Ultraviolet radiation bathes the surface without an ozone shield, and impacts vaporize any nascent organics. As this part closes, Earth emerges battered but resilient, with a moon companion and nascent oceans. Yet beneath the waves, something stirs. Chemical soups bubbling in hydrothermal vents. Could these hellish depths cradle the spark of life? Or will freezing doom it all? Ever wondered if our blue planet could turn into a giant ice ball, frozen from pole to equator, trapping life in a cryogenic prison? Sounds like sci-fi, but it's Earth's real nightmare phase. Building on the post-impact rebirth, we're plunging into eons of glacial Armageddon. This is where geology meets survival horror. And by the finale you'll ponder, did these deep freezes forge the path to complex life, or nearly snuff it out? Enter the Archean Eon, 4 to 2.5 billion years ago. Earth cools. A solid crust blankets the globe, with oceans expanding to cover 70% of the surface. Plate tectonics ramps up, subducting slabs and birthing volcanic arcs. The atmosphere? Still CO2 heavy, but methane from early microbes adds warmth. Zircons from Jack Hills, Australia, reveal weathering and erosion, implying rain and rivers sculpting land. Life ignites around 3.8 billion years ago. In hydrothermal vents, black smokers spewing mineral-rich hot water, RNA world precursors form self-replicating molecules. Stromatolites in Greenland and Australia, dated to 3.7 billion years ago, show cyanobacteria thriving, photosynthesizing without oxygen release initially. But by 3.2 billion years ago, oxygenic photosynthesis evolves, a game changer. Cue the Great Oxidation Event, peaking 2.4 to 2.1 billion years ago in the Paleoproterozoic. Cyanobacteria pump out O2, oxidizing iron in oceans to form banded iron formations, vast red deposits in Minnesota and Australia. Methane oxidizes too, collapsing the greenhouse and triggering the Huronian glaciation, Earth's first snowball episode around 2.4 to 2.1 billion years ago. Ice sheets engulf continents. Only volcanic CO2 buildup thaws it after millions of years. Fast forward to the Neo-Proterozoic, 1 billion to 541 million years ago. Supercontinent Rodinea's breakup intensifies weathering, sucking CO2 from the air. Combined with a dimmer sun, it sparks cryogenian glaciations, four snowball Earth events from 720 to 635 million years ago. Earth freezes solid. Models from Harvard's Paul Hoffman show ice up to a kilometer thick, with open water only at equatorial vents. Life clings on in meltwater pockets or under ice, evolving survival strategies. The thaw? Volcanic eruptions release CO2, building to extreme greenhouse levels. Cap carbonates, limestone layers, cap glacial deposits worldwide, evidence of rapid warming. The Ediacaran period follows, 635 to 541 million years ago, with soft-bodied organisms like Dickinsonia appearing in fossil beds from Australia to Newfoundland, precursors to animals. Earth's core hums, its magnetic field shielding from solar wind. Continents drift, setting stages for future supercontinents. But as ice recedes, a biological revolution brews. Wrapping up, these frozen ordeals tempered Earth, oxygenating the air and priming for diversity. Yet what explosion of life awaits in warmer seas? Will it conquer land or face annihilation? What if a single evolutionary leap turned microscopic blobs into a riot of claws, shells, and fins, rewriting Earth's biosphere overnight? Fresh from icy thaws, we're exploding into the Phanerozoic, the age of visible life. This is evolution's blockbuster, packed with twists. Hang on. By the close, you'll ask if mass die-offs were curses or catalysts for us. The Cambrian explosion, 541 million years ago, kicks off the Paleozoic era. In Burgess Shale, Canada, and Chengjiang, China, fossils reveal a burst. Trilobites with compound eyes, anomalocaris predators, and early chordates. Why? Rising oxygen enables larger bodies. Predation drives armor evolution. Oceans teem. No land life yet. By 470 million years ago, fungi and plants colonize shores, their roots weathering rock to soil. Arthropods follow, millipedes, scorpions. Tiktaalik, a 375 million years ago fish tetrapod hybrid from Ellesmere Island, crawls onto land with limb-like fins. Amphibians dominate Devonian forests. Carboniferous period, 359 to 299 million years ago. Swampy coal forests birth giant insects like Meganeura, 2-foot wingspan, in oxygen-rich air, 35% versus today's 21%. Reptiles emerge with amniotic eggs, conquering dry lands. Permian-Triassic extinction, 252 million years ago. The Great Dying wipes 96% of marine species, 70% terrestrial. Siberian traps volcanism releases CO2, acidifying oceans and warming climate to 104 degrees Fahrenheit. Survivors? Tiny, adaptable forms. Mesozoic dawns. Dinosaurs rule from 252 to 66 million years ago. Pangea splits. Flowering plants explode 140 million years ago, co-evolving with insects. Oceans host ichthyosaurs, skies, pterosaurs. Mammals lurk small and nocturnal. As this era peaks, an ominous shadow looms, a space rock hurtling toward doom. Concluding this part, life's tapestry weaves through triumphs and tragedies. But could a cosmic bullet end the dinosaur reign and pave our path? Could the fall of giants like T-Rex open doors for furry underdogs to rule Earth, and eventually for us to ponder our own origins? From Mesozoic ashes, we surge into the Cenozoic, Earth's latest chapter. This finale ties the epic. Suspense peaks as we face today's threats. But first, the ultimate hook. What future awaits our resilient planet? The Cretaceous-Paleogene extinction, 66 million years ago. Chicxulub asteroid, 6 miles wide, strikes Yucatan, Mexico. Debris blocks sun. Deccan traps volcanism, adds sulfur aerosols. 75% species vanish, including non-avian dinosaurs. Evidence? Iridium layers worldwide, shocked quartz. Mammals explode. From shrew-like survivors, primates emerge 56 million years ago in Eocene forests. Grasses spread 20 million years ago, fueling savannas and herds. Himalayas rise from India-Asia collision, altering weather. Hominins branch 7 million years ago in Africa. Australopithecus walks upright. Homo erectus masters fire 1.5 million years ago, migrates out. Neanderthals, Denisovans mingle with sapiens approximately 300,000 years ago. Ice ages cycle. Humans domesticate crops 12,000 years ago, build civilizations. Today, Earth thrives with 8 billion humans, but Anthropocene impacts loom. Climate change, biodiversity loss, a potential sixth extinction. In closing, from a dusty nebula to a living world, Earth's 4.54 billion-year odyssey proves one truth: resilience defines us. Yet as stewards, our next chapter is ours to write. Will we nurture this cosmic gem or risk its unraveling? The story continues with you.